The virtual file system supports several key abstractions. First, there is obviously the file abstraction. These are the elements on which the virtual file system operates. The OS represents files via file descriptors. A file descriptor is created when the file is first opened, and there are a number of operations that can be supported on files by using the file descriptor to identify the specific file. These include read, write, lock a file, send a file, also close a file ultimately. For each file, VFS maintains a persistent data structure called an inode. One of the information that's maintained in this inode is the list of all the data blocks that correspond to this file. This is how the inode derives its name. It's like an index node for that file. The inode also contains other pieces of information for that file, like permissions, the size of the file, whether the file is locked, etc. The inode is a standard data structure in Unix-based systems, and again, it's important because the file does not need to be stored contiguously on disk. Its blocks may be all over the storage media, and therefore it's important to maintain this index. Now, we know that files are organized in directories, but from the virtual file system's perspective, and in general from Unix-based systems perspective, a directory is really just a file, except its contents include information about files and their inodes so that we can find where are the data blocks for these files. And so the virtual file system will interpret the contents of the directory a little bit differently. To help with certain operations on directories, Linux maintains a data structure called dentry, stands for directory entry, and each dentry object corresponds to a single path component that's being traversed as we are trying to reach a particular file. For instance, if we're trying to reach a file that's in my directory, in the directory named ada, we would have to traverse this path, /users/ada. In the process, the virtual file system will create a dentry element for every path component, for /users, that's the second directory in this path, and then finally for the third directory in this path, /users/ada. Note this first slash, that corresponds to the root directory in the file system structure. The reason that this is useful is that when we need to find another file that's also stored in this directory ada, we don't have to go through the entire path and try to reread the files that correspond to all of these directories in order to get to the directory ada and then ultimately to find the next file that we're searching. So the file system will maintain a cache of all of the directory entries that have been visited, and we call that the dentry cache. Note that this is soft state. There isn't some persistent on-disk representation of the dentry objects. This is only in memory maintained by the operating system. Finally, there is the superblock abstraction that's required by the virtual file system so that it can provide some information about how a particular file system is laid out on some storage device. This is like a map that the file system maintains so that it can figure out how has it organized on disk the various persistent data elements, like the inodes or the data blocks that belong to different files. Each file system also maintains some additional metadata in the superblock structure that helps during its operation. Exactly what information will be stored in a superblock and how it will be stored differs among file systems, so that's why we say it's file system specific information.